I noticed about the youth beyond कर दिए कि नहीं? अच्छा चलो we start studying. Okay, so we did talk about binding energy before. I want to talk about it a little bit more. Okay, so we talked about the simple concept of binding energy. You're all familiar with this concept, right? Okay, what is binding energy? Let's see, मेरी तार. Wait. अच्छा ये कहाँ से है? Okay, energy equal to? No, it's E is equal to mc squared, right? So mass deficit multiplied by the square of okay, fine, but yeah, okay, so the difference in mass is converted into energy. That's the concept behind binding energy, and this is the concept that leads to reactions like fission and fusion, which are a huge source of energy. Okay, so we had the simple formula in which we equated the masses of the nucleons, and then we subtracted them from the mass of the nucleus, and we saw the difference in the mass that you are calling the mass deficit, and then multiplied that by c squared to get the binding energy. That's one kind of formula. There's another formula. You know, the same topic, different people have worked on it in different levels of detail and using different tools. So there is another formula which is known as the semi-empirical binding energy formula. So semi-empirical, हाँ पढ़ा था हमने, आज मैंने थोड़ा सा इसको explain करना है, ठीक है? उस दिन मैंने पढ़ाया था आपको, but now there are some terms in the formula, I want to explain those, okay? Binding energy, actually do you know what? There is no topic that's that we can cover from, we can say we've covered everything about it. It's never like that, right? You can always go in as much depth and as much detail as you like, okay? So I can stop there where I stopped last time, or I can go a little bit further, okay? So hello, we were missing you. It's okay, don't worry. Okay, you remember this formula, right? This formula has a number of terms that we were talking about, and these terms are, we explained these terms last time, okay? So for example, we have this which is related to the volume, we call it the volume term, okay? So volume term. So volume term gives us insight into the properties of the nuclear force. So this gives us insight into the properties of the nuclear force, okay? So please make them of about 10 minutes each, okay? So if every nucleon is attracted to all the other nucleons, what is the nucleus? The nucleus is a combination of all the nucleons inside the nucleus. Now if these nucleons are particles and they can attract each other, right? Okay, so if every nucleon is attracted, then binding energy should be proportional to A into A minus 1, which is approximately equal to A squared, okay? But from this we see that it is not proportional to A squared, rather binding energy is proportional to A. So that shows a discrepancy, right? So, this suggests each nucleon attracts only its closest neighbors. Okay? Not all of the nucleons like we said before. Okay? So, that is one observation, right? That is one point we can note from here. You can imagine a nucleus contains a number of nucleons. The bigger the nucleus, like let us say uranium is a very big nucleus with a lot of nucleons. So, will this nucleon, one single nucleon inside the nucleus be attracted to all other nucleons, or like we said just now, no, we think it is attracted only to its closest neighbors. Okay, that is one point. A into A minus 1 लिखा है ना, तो minus 1 if we assume that A is a large quantity, then minus 1 will not make much difference, will it? Approximately लिखा है ना. देखो it's simple है ना, देखो 1 is a small number as compared, you get that, right? So, if we consider 1 to be negligible, then this is A and this is A and this is, yes, 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 okay. So each nucleon has about the same number of neighbors, each nucleon thus contributes roughly the same amount to the binding energy. Okay. So, even if you have a large number of nucleons like in the case of uranium, but if we are saying that all these nucleons do not have an effect on one single nucleon, it is only affected by its closest neighbors, then we can assume that every nucleon will more or less experience a similar force. So, let me also write this because then it will be easy for the students who are studying online to follow. Same number of neighbors, each nucleon thus contributes roughly the same amount to the binding energy. Okay? Except there is an exception. You see, it is very interesting. Mathematics, for example, sometimes when we study mathematics, it becomes abstract, right? But we as physicists, the fun part I find, and I am sure many of you find, is the fact that we actually give a meaning to that mathematics, right? When you are studying mathematics just on its own, it has a beauty for sure, but many times it is just you are solving abstract problems that you cannot imagine physically, right? But when you relate that mathematics to a physical phenomena, I think it becomes much more meaningful. So that is what we are doing now. We are relating the mathematics to the physical interpretation, explanation, and trying to understand why we have each of the terms in this equation. So I think that is interesting. Now, we talk about nucleons, we talk about the attraction felt by a single nucleon in the nucleus, and then we said that one single nucleon on the basis of this explanation is influenced by its closest neighbors. But there is an exception. What about the nucleons on the surface of the nucleus? the nucleons on the surface of the nucleus will have a lesser number of neighbors, है ना? So therefore the level of attraction they will experience will be less. So let us write this. I am writing it because it will be easier for